Okay, so this is the third one of these motion graph videos I've made. Motion graphs can be sort of confusing because they're not really intuitive. Sometimes you can't just look at them and interpret the data, and the reason is because if I have something like, say, this graph right here, displacement on the y and time on the x. If you're asking me some kind of question where you want to know where does the displacement increase or something about displacement, we can just use the y-axis to figure it out. Or if you're asking me for time, we can use the x-axis to figure it out. But a lot of times what you're given is you have something like a displacement and time graph, but they're asking you to figure out velocity. So it's really not one of the components of the actual graph. So you have to, you really have to be able to manipulate the graph. So I think if we get through this one and the other video that I did, this should be pretty straightforward. So, all right, so let's see if we can kind of work our way through some of these problems here. A cart travels with a constant non-zero acceleration along a straight line. So that means it's moving in a straight line, but it has some sort of constant acceleration, like say 2 meters per second, okay? 2 meters per second squared. And then we're going to say, well, which graph best represents the relationship between the distance the cart travels and the time of travel, okay? So what we're using here, we have a distance versus time graph, but we're asking to use the distance versus time graph to find out the acceleration, okay? And so the easiest thing to do is to kind of look and see, well, what's actually happening in these graphs, okay? So the first one, you have this distance versus time, and distance divided by time would be velocity, right? And so with this one, you can kind of see that if I was just to take slope, which was distance divided by time, and remember the rule with motion graphs, if you can get y divided by x to equal what you want, that means you just take slope. If you get y times x, that means you use area under the curve. And so this is y divided by x, as in m divided by s is going to equal velocity, right? Well, that isn't quite what I want, but if I think about this, if it was an increase, if somehow the velocity was getting faster and faster, it would be sort of exponential, right? If it was a straight line like this one here, this is velocity, right? The distance keeps increasing as time increases. And so you could say, well, you have a constant velocity here. Well, constant velocity means that there's no acceleration, okay? With this one, you have, if you're looking at this and you're saying, well, it started out at a certain distance, it went up and then slowed down. So that doesn't really imply constant acceleration, okay? So this also doesn't work. This one here, you have a constant velocity. Now, this one, it's slowing down, but it's a constant velocity, which means that you don't have acceleration. But this one, you have this exponential curve, and if you remember that acceleration is meters over second squared, okay? It doesn't take much to take a look at this and think that this has to be some sort of acceleration curve. So anytime you have distance and time, and you're looking for acceleration, you're always looking for some sort of exponential curve, either in the downward direction or the upward direction here. So this would be our answer to this when I'm looking for acceleration. Okay, so next one, a car is on a straight road. It starts from rest and accelerates at 1 meters per second for 10 seconds. Then the car continues to travel at a constant speed for an additional 20 seconds. And then we want to determine the speed at the end of the first 10 seconds. So right away, my clue is I'm using some sort of kinematics equation because I have acceleration. Acceleration is, let me do this way. Acceleration is equal to 1 meter per second squared. I have time. It equals 10 seconds. It starts from rest, so that means I have velocity initial, or for the IB folks, S, or U rather, and that's going to equal 0. And then I want to know what the speed at the end. So I want to know what my velocity final is, okay? And so I have 1, 2, 3, 4. I'm missing distance, or S or D. This is very confusing with IB, but that's okay. We can work through that because we have big brains. And so what I have is acceleration, I have time, I have an original velocity, and I have final velocity. Okay, and so when I want to go through that, I want to be using just a simple kinematics equation. And so if we use velocity is equal to u plus at, and then remember this u is velocity original, it's pretty easy to calculate. So our original velocity is 0 meters per second. And then we're going to add in our acceleration of 1 meter per second squared, and we're going to multiply that by 10 seconds, okay? And so our answer is, our velocity is equal to 10 meters per second. Okay, on the, excuse me, on the grid below, use a ruler or straight edge to construct a graph of the car's speed as a function of time for the entire 30-second interval. So I'm using speed or velocity in this, on the y, and then time. So we determined that the velocity is 10 meters per second for the first 10 seconds. So I'm not going to use a straight edge, but I can get it as straight as possible. So for the first 10 seconds, you just have this constant increasing velocity. Acceleration, we figured out already, was 1 meter per second. And then that's for the first 10 seconds. And then the car travels at a constant speed for an additional 20 seconds. A constant speed means it's going 10 meters per second for 20 more seconds. All right, simple enough, okay? Then the next question is calculate the distance the car travels in the first 10 seconds. So this is when we're gonna use our meters per second and time. Now if I take the y and I multiply it by the x, as in meters over seconds times seconds, look what happens. If I do that, that goes away and it's meters. That's what I want, is meters. So this implies that since my y times my x gives me my answer, that I'm going to use the area under the curve. There's a couple ways of doing this. We could use kinematics, but I prefer just to use simple geometry. And since what I want is this area right in here, the first 10 seconds, we can use the triangle formula, which is going to be 10 times 10 times 1/2, and so 1/2 of 10 times 10 is equal to 50 meters, okay? So I tend to use, on these graphs, I'll tend to use just the triangle formula and then the square, right? So it makes it simple. You just add up a couple of components. They're pretty simple that way. Okay. Let's take a look at this next one. A student throws a baseball vertically upwards and then catches it. If vertically upward is considered to be positive direction, the positive direction, which graph best represents the relationship between velocity and time for the baseball? Okay, so what we're looking at is a baseball that goes up in the air and then comes back down. So it's got this positive velocity and it's got this negative velocity. Now, it's not going below the area that it started from. So the first thing I can say is that I don't have to worry about going in different directions when I'm doing this, but let's see what happens with this. This one is that my velocity is starting at 0, it's increasing, 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 and then starts to decrease, right? The thing I'm going to say is if you're throwing a ball up into the air and it actually goes upwards, you have to start with a pretty strong velocity, a pretty high velocity, and then it starts to slow down. So anything going up is not going to work. Okay, so this one isn't going to work either because the velocity did not start at 0. You can't get a ball to go up in the air if you don't put some sort of force into it and make the initial velocity actually be less than the final velocity when it reaches the top. So both those are gone. So it's going to be one of these two. Now this one is implying you start off with this really a strong velocity, a really fast velocity, it reaches the top, and then the velocity starts to increase again, but in the positive direction. And what's happening is the velocity is starting out at a high velocity, slowly decreasing until it hits the top, and then increasing velocity, but in the negative direction. And so what you want is this one right here. I start off with, say, 10 meters per second, it reaches the top at 0, and then it's 0 velocity, but it goes in the negative direction and then increases to whatever speed I have at the end here, 10 meters per second negative. So this is our answer. So sometimes just looking at the graph and starting to interpret it is helpful. All right, the graph below represents the displacement of an object moving in a straight line as a function of time. So I have m and I have s. What is the total distance traveled by the object during a 10-second interval? Now this one is one you should take a little note about, okay? Because this can be a really tricky little graph. Now it's asking for displacement, so that means that I have displacement right here. Actually, it's asking for distance, but I have displacement right here. I can't take y divided by x and get my answer, so I'm not going to use slope. I can't take y times x and get my answer, so I'm not going to use area. But if it's just asking me for distance, all I have to do is just figure out what's happening on the y-axis. But look what they're asking. They're asking for distance. So if the answer was displacement, remember that distance is the total length traveled during the time that something is moving. It isn't asking, this isn't asking you for the displacement as in it started here and ended up here. It's asking you how far did it go as it slowly increased and increased and increased and increased in this direction, and then it went this direction. So I'm going to look at this and I'm going to measure first where does it end at 10 seconds during the 10-second interval. So it ends up right here, right? There's my 10-second interval. Between 0 and 8 seconds, it went 16 meters. Between 16 meters, or 8 seconds and 2 seconds, it went 8 meters. Now, if it was displacement, my answer would be 16 minus 8, because up is positive, down is negative. But distance, you just add the total distance that you covered during your journey. 16 plus 8, so this is 24. So this is distance. This is displacement. And this will come up again at some time during your physics careers, so don't forget it. Okay.